Virginia Tech campus in Blacksburg, Virginia, and I'd like to welcome everybody to CUAHSI's 2018 Winter Cyberseminar series called Urban Stormwater Hydroinformatics. We're going to be doing the first Wednesday, 1 to 2 p.m. cyber seminar here from Virginia Tech called Developing and Utilizing Stormwater's Big Data Set. And I'm hoping everybody can see the screen. Next week, Branko Kirkes from the University of Michigan will be doing Enabling Smarter Urban Watersheds. In 2 weeks, Ben Hodges from the University of Texas will be talking about urban hydrology in the National Center for Infrastructure Modeling and Management. And in 3 weeks, D.WRE from Colorado State will be talking about watershed scale effectiveness of green infrastructure. I want to point to the bottom of the screen in red. So if you have questions or comments during the webinar, we're going to hold those to the end. And you can type in the question chat box at the bottom, and our moderator will read those out, and we'll do our best to answer those. Our goal today is to do a discussion, really, for about 45, 50 minutes, and leave about 10 or 15 minutes at the end. So let's see if we can get this thing going here. All right, so our title slide. I've got with me today Dr. Marcus Aguilar. Worked with Marcus for the last 6.5 years through his master's and PhD, and then as a research scientist in my group. And Marcus is just starting a new job with the city of Roanoke. And Marcus, you'd say hello.
Hey, everybody.
And Dr. Clayton Hodges. And again, Clay has worked through his PhD here in my research group, but Clay has gotten his BS and master's degree at Virginia Tech, and then owned his own consulting firm locally here for the last 20 years before he also got his PhD. Clay?
Good afternoon, everyone.
And instead of activating the video, we felt we'd be a little less formal and show you a selfie we just took yesterday. And so here we are, the old man Randy on the left, and Clay in the middle, and Marcus on the right. So that's your selfie. So some initial thoughts, and this is really a discussion more than a lecture of any kind, and kind of in the way that the famous bluegrass musician Doc Watson used to open up his concerts of welcoming you into his living room. We'd like to welcome you into my office, where Clay, Marcus, and I over the last 6.5 years have often had some high-level discussions and detailed discussions, honestly, of urban stormwater, hydroinformatics. So we're just going to have a discussion, and we may interject and talk over each other once in a while, but we often have had these kind of discussions. In terms of the audience, I understand that many of you come from different backgrounds, and that's wonderful. This is a very wide-ranging topic that we're talking about. We do have a lot of commonality, and I think our work objectives are very similar. We all want to improve the water quality and reduce flooding, improve the ecosystems of our urban areas, and that leads to the improvement of the quality of life in the communities in which we work, live, and play. So that means we're working on ideas and processes and technologies that's going to improve the life in our urban areas, which of course comprise more than 80% of the U.S. population. This type of research that many of us, probably most of us that are listening, comprise a mixture of the sciences and engineering, traditional hydrology and hydraulics, environmental engineering, but also stepping outside of those boundaries, such as economics, political science, land use, land development, social science, things like environmental justice, education, quality of life, lots of different areas combined here, which is just a lot of fun. And in terms of the data, there's just a lot of things we have to consider with space and time resolution. So the processes that we study are driven by small-scale changes over vast areas. Think about parcel development leading to urban sprawl. So the data that we use to evaluate the effects of these changes must be at an appropriately fine scale, which necessitates spatial data that provides information at sub-meter accuracy, like raster data, and then vector data sets that appropriately schematicize real-world features such as parcels and storm drains and manholes, and so on. The water quality and quantity data that we collect must likewise be in an appropriate space and time resolution. Things like illicit discharges, which can only be detected if sensors are well distributed throughout a watershed. Monitoring hydrograph, polutograph flashiness, which means we have to observe things at much less than an hour timescale. And precipitation data, which varies dramatically in space. We need very dense rain gauge networks. And grab samples are no longer defensible. A lot of things that we have to pay attention to. So as we look down what we're going to talk about today, we're going to do, since this is the first of four, we're going to do an introduction to the topic of urban stormwater hydroinformatics. We'll talk about water's big data, developing that big data, and using that big data. And then we'll open it up for any questions you might have. And I'm going to turn it over to Marcus for some of the introduction.
Thanks, Randy. The graphic that you see on your screen now is data from the United Nations 2014 World Urbanization Prospects Report, showing the increase in the percent of the population living in urban areas between now and the year 2050. You'll notice the blue line at the top of the graph. There will be a estimated 82 million additional urban dwellers here in the U.S. That gets us almost to 90% of our national population living in urban centers. And globally, it's expected that there's going to be an additional 2.3 billion people living in these denser urban centers. So the result of this process of urbanization, of people moving into these urban cores, of course, is land development. So we see from this false color imagery of impervious surface area in the Washington, D.C. area, the 1984 impervious cover and the 2010 impervious cover, which shows us, for example, what happens when you have lots of people moving into these metropolitan areas. You have this changing land cover from prairie grass and forest and agricultural land into harder, more impervious areas. So let me also mention that the movement into cities is not all the mega city. It's not all the New York City and the LA and the Houston. It's a lot of smaller, so medium and smaller areas across the U.S. and of course globally. The UN report estimates that a large amount of this urbanization will happen in the 500,000 population range. So we see more cities across the U.S. The map that I have shown here on the screen is a map of the regulated entities under the NIPTE's Municipal Separate Storm Sewer System Program, or the MS4 program. You can see there's about 850 larger MS4s. So that's part of the Phase 1 program, which began in 1990. And there's fewer of those, of course, and the regulations are a bit more extensive for those localities. And then in 99, the Phase 2 of the program began and brought in an additional 6,700 approximately localities across the U.S. So I'm going to note again here that even though it looks like most of the land area of the U.S. is not incorporated in this program, it comprises greater than 80% of our national population. So when we talk about urbanization, of course, we think about the land cover change, we think about development, urban sprawl, shopping malls, strip shopping centers, and so forth. And this leads to various land cover effects, but also other effects on streams and rivers that flow through these areas. So as an example, I have shown here a photograph from Roanoke City. It's a locality about 45 minutes up the road from where we are here at Tech. This photograph was taken in 1928. It's a spring, sort of a headwater spring that's near downtown Roanoke. And the picture I have shown here is the same spring and stream system taken just last year from the same perspective. You can see that the white SUV there is parked just on top of where the stream used to be. The the spring is somewhere behind the building there in the background. So you see kind of a disappearance of rivers and streams and springs and other hydrography in urban areas. In cities, in this particular instance, for example, but you see this at a larger scale in other areas, and we'll show you some graphics of that later on. Here's another photograph just for more examples of the same stream system, a little bit further downstream there in Roanoke City. And as we start thinking about the watershed effects of the land cover change and then the burial and disappearance and fragmentation of these stream systems, what we see is just fundamental changes. So we're going from open streams. This is a schematic from some historical research we did on the same stream system I showed you previously, to tunneled, channelized systems. So we're going from, again, open sort of natural stream and spring systems to pipes, channels, concrete line systems. So again, land cover change and stream and storm drain change over time. Here's a similar example from another locality just up the road, the city of Charlottesville. The zoomed in graphic you can see there showing Meadow Creek on the right shows the open areas of the stream in blue and the covered areas in like an orange color. Similar idea, just showing the fragmentation of the riparian ecosystem across the city. I know that other similar projects on buried streams are happening in city of Baltimore and in other places, but a really important and fundamental effect on our urban watersheds. So what happens when we have these changes that occur over long periods of time, this development and these stream hydrography changes? Of course, the ones that we typically talk about would be flooding. So we have increased peak flows and volumes of runoff coming off of our watersheds into our streams, as shown, for example, in the photograph from Houston, Texas, after Hurricane Harvey this year. With that increased flooding, we also have increased concentrations of various pollutants that we had that we didn't have previously, so metals and organics and nutrients and solids and so forth. And with those, we have the degradation of stream and watershed ecosystems via the loss of habitats and the smothering of stream substrate.
Okay. So what is hydroinformatics in any case? So we've talked about urban stormwater. So hydroinformatics, which has the ability to impart knowledge. Well, in other words, let's measure things. Let's measure everything. Our society is certainly something that we see every day, measuring, how much do we walk? You've got your phone in your pocket. How many steps have you taken? We are measuring everything. So having to do with water, so hydroinformatics. So I've got a few photos here, and Dr. Kirkes next week will talk all about this. But on the bottom left, this photograph is an on-campus here at Virginia Tech system that we've got called LUAS, Learning Enhanced Water Assessment System. We've got a weather station, we've got a webcam, we've got a water quality sonde, we've got acoustic Doppler velocimeter. And so we're taking measurements, in some cases 1 minute for some of it, 3 minutes for the rest of it. And we can tune into that with our smartphones or online on a web browser. And this is great. So we can use that for teaching purposes. On the right side, we've got a typical USGS stream gauging station. And up in the middle there, we've got an ISCO 2150 acoustic Doppler flow sensor. And you can see a bunch of detritus that's hung up on the cord there. One of the dangers in the storm sewers here in Blacksburg. So we're measuring things. It's what we want to do. On the left-hand side of this slide is some of the data that we've recorded at the LUAS station. The URL for the LUAS station, if you're interested, is there at the bottom on the left. But notice, because we're taking real-time measurements or near real-time, we get some real interesting data back. The blue line is showing the change from a thunderstorm in temperature. Over 3 minutes, we got nearly 5 degrees centigrade. That's really dramatic change, not something you would see if you were doing grab sampling. in flow in green, notice that in 10 minutes we saw a 72 times change in flow. So the photographs are showing you base flow on the right and flood stage on the left. I'm going to show you a short clip here. I get this thing running. This is a time lapse from September 2016 at that same station on campus. This is off of a 690-acre urbanized watershed, about 95% urbanized right here in town. And on the left, you can see the data that's recording. And the blue line is the accumulated rainfall. So a serious thunderstorm came all at once, ran off all those impervious surfaces. The green line is the water temperature. You can see that pretty rapid rise in temperature. Again, same point on campus. This, instead of flow event, this is a turbidity event. October 2014. Again, not something that you would capture or even notice unless we were watching the data and saw that the turbidity had changed dramatically. So what's happening? We've got sensors out there, we're collecting data. And that data is indicating something. Well, it's just a lot of data. If we're collecting at 1 minute intervals, it's a lot of data. Well, it's not really useful unless we do some analysis on that data and turn it into information. You know, some of might have some outliers, might have some bad data. A probe might be uncalibrated for a while. We might have something that's knocked it ajar. So we've got to go through that and turn it into information, which is going to help our decision-making process. And with that, we can make some investments in the watershed, whether it's stream restoration or whatever it might be. And then we can go back and say, okay, with more information based on that investment, was it good? Wasn't it good? So this turns into our adaptive feedback loop. And the important thing to realize is that uncertainty is always part of the answer. So don't forget about that. We don't forget about it. I'm sure you don't either, but that's why we've kind of smudged those little boxes there. Okay, so with that as kind of an introduction to the hydroinformatics, I'm going to talk about, well, now what's big data? So I'm going to use two examples here, the National Water Model, and then get into our topic of urban storm infrastructure inspection, monitoring, and other attributes. So I'd like to thank both David Maidman and David Arctur for the next couple of slides. So what is the National Water Model? So here's basically what's going on at the National Water Center in Tuscaloosa, an aggregation of the NOAA river forecasting centers, getting all of that information and combining that with the National Elevation Dataset, the Watershed Boundary Dataset, National Land Cover Dataset, and the National Hydrography Dataset, and creating 2.7 million reach catchments so that we can basically go from what was, basin hydrology modeling to reach catchment. And so take, in essence, on the left, what had been two basins and one forecast point to 130 catchments and now flow lines. So we've gone from watershed to continental hydrology. That's a lot of data. That's big data. This graphic is really before the whole model was operational. You can see in the bottom right there, this was May of 2015. And you can see the pulses running through this. It's all color-coded. Look at the legend there for flow. Again, this is big data. This is river and stream data showing across the continental U.S. This is not urban data per se, but it is one of the examples of big data for water. Now let's take a look at the urban scenario. This is from my friends in Baltimore. Really sky-high view. I said, well, what do you got for infrastructure? Oh, we got a lot of infrastructure. Yeah, here it is. Oh, okay, well, I love this photograph. Yeah, this is from when some of the underground pipes were built, and we don't know when they were all built, they told me. Well, of course you don't. They were built over decades, in fact, centuries. So here's some of the statistics from Baltimore. Over 1,100 miles of pipe, over 100 miles of streams, more than 52,000 inlets, 27,000 manholes, 1,700 outfalls, pump stations, a lot of infrastructure. Fairfax County, one of the organizations that we work with. Let's zoom down a little bit and look at the detail. This is just one section of their infrastructure. Those of you familiar with this area just west of DC, that's Route 66 cutting through there. So we've got a lot of not just pipes, but nodes, manholes, inlets, catch basins. Here's another section of Fairfax County's infrastructure, and yet another section. So what do they have? More than 1,600 miles of pipe. With their inspection information, 20% of that is more than 45 years old, 5% in a state of failure, 20% is significantly deteriorated. More than 62,000 structures, 20 state-regulated dams, 6,100 stormwater control facilities, and they valued their system at $1.3 billion. And we're just talking about the infrastructure at this point. Not all the attributes, not all the workflow that's going on for maintenance and inspection and monitoring and things like that. And we haven't touched upon all the other phase ones, whether it be Philadelphia, Boston, Chicago, Houston, LA, right? And what about the smaller MS4s, the phase twos that we saw in a map that Marcus mentioned earlier? There's an awful lot of money that's being expended right now for all of this. So I'm going to turn it over to Marcus again to talk about, what are we doing in the urban environment?
Thanks, Randy. So from the perspective of a stormwater manager, there's a lot of different operational and big picture things that have to be considered in order to do your job well. So one of the main points, the first one there, is just the quality of life in your community. So a lot of local governments and regional and state government officials, they're trying to and desiring that their communities would be great places, as we said earlier, to live, work, learn, and play. And again, that's a big picture goal. So working towards that from an urban stormwater standpoint takes some really nitty-gritty detail and boots on the ground, and some of that is what we'll be showing you here in the next couple of slides. So to do that, one of the important things is to know how much infrastructure you have and where is it. So that would be, of course, asset management, which is the second bullet point. What is the condition of it, and how and when will it need to be replaced? So maintenance and replacement. And as it does need to be replaced and upgraded, capital investments. How does a locality or regional government plan for and prioritize infrastructure investment over long time horizons? Going with that, of course, is the problem of funding. So being able to raise support for a stormwater utility, for example, as utility fees or taxes. This infrastructure is, of course, very expensive. So understanding how much of it you have and where it is, and when it will need to be replaced and upgraded, is, of course, a critical piece of information for the funding and investment question. In addition to these decisions, a stormwater manager will typically be required to comply with various regulatory programs. So as I mentioned earlier, the NIFTY's MS4 program there, the first sort of sub-bullet point that you see, requires a kind of a suite of programmatic stormwater control measures. So that would include nutrient management plans at municipal facilities, public education and outreach, monitoring outfalls, so the location where the storm drain empties into the stream. You see a photograph of one of our colleagues at Roanoke City. They're doing just that. In addition to those requirements, there's going to be, in many cases, requirements of the total maximum daily load program, where local governments and regional authorities will have to demonstrate progress towards waste load allocations of various types, so nutrient, sediment, and so forth.
Let me just point out, Marcus, again, we often just go back and forth on these discussions, but, in a report put out by the Virginia legislature couple of years ago, the Senate Finance Committee, the Chesapeake Bay TMDL, estimated that the total capital cost to satisfy the Chesapeake Bay TMDL was between $9.4 and $11.5 billion. That's capital cost, with estimated annual cost of $1 to $1.2 billion. So my point being that there's a lot of money being spent in urban stormwater. And this is just Chesapeake Bay TMDL.
That's good. And of course, we have TMDLs nationally in the Tahoe Basin and various other places throughout the U.S. that have similar economic impacts. The third bullet point there, the FEMA Community Rating System, is not quite a regulatory program, but it's still something that a lot of communities will be engaged in. And a lot of that has to do with developing high-quality flood mitigation measures, with the outcome being the reduction of flood insurance premiums for their citizens. So it's a really great thing for communities to be invested in, but of course, just like all these other programs, takes a considerable effort, and with that, as we're talking about with this presentation, really high-quality data to go with that. Other local government efforts, of course, would be local policies and incentives, so zoning ordinances, impervious cover requirements, stormwater utility fee, so stuff like that, and community engagement, of course, is the last bit of that. So working with the community to understand why we want to reduce flooding and improve water quality. And you can see some nice photographs there on the bottom of the screen. So for these efforts, there's, as I mentioned, a large amount of big data required. I'm going to go through a couple different types of big data that we would typically use in urban stormwater. The first, of course, is going to be time series water observations. And again, Dr. Kirkes will probably talk about this at length next week, but just wanted to kind of mention these things. So we would typically measure flow depth and discharge at a minutes scale. Again, we're not talking anymore about daily discharges. We need information at a higher time resolution than that because of the flashiness of hydrographs. The same with turbidity, pH, and these other water quality parameters that you see listed there. These water quality events happen rapidly in urban areas, and so we need to be able to take measurements at a time scale that's appropriate for actually capturing these events. And indeed, the LUA station, as pictured there at the bottom of the screen, does just that. We also need weather data at an appropriate time and space resolution. So rain gauges placed throughout our watersheds that will give us the information really that we need to make decisions about flood alert and warning and planning for similar flood events in the future. And then, of course, the fourth bullet point there is constituents that we're really not able to measure with sensors, but constituents that we actually have to use an auto sampler and collect samples for, again, at higher time resolutions than we used to. This is not it is sort of a grab sample, but the resolution is much higher than it used to be. The fourth is, of course, aquatic insect, the benthic macroinvertebrate component of stream monitoring. This is not something that you can do with a sensor, so it's still something that we have to go out in the field and do on a usually biannual basis. But it is also part of the urban stormwater suite of data that we really have to have. In addition to the time series data, we also need a substantial data set on the land surface. So the graphic that I have shown here is 1 meter data provided by our state geographic information network, showing land cover at, again, 1 meter resolution. Soils and topography are also typically integrated to do hydrology calculations in our watersheds. This graphic here is showing LIDAR or a DEM generated by LIDAR data, again, in Roanoke City, Virginia. You can see the topography of that watershed, and the drainage system, which I'll talk about here in just a second, is overlaid on top of that. As I mentioned, the stream and the storm drain are important facets of understanding drainage in urban areas. The location, of course, is important, and understanding the way that the system is connected and the direction of flow as you map these systems out is sort of the second tier of data quality there. And of course, the highest tier of data quality would be engineering type details, so dimensions and materials. That's really possible only if you go out in the field and actually map these systems out, which we'll discuss shortly. The value of these data sets is that you get to sort of dissolve the watersheds or break the watersheds into smaller sub-watersheds, or catchments as we like to call them, to do hydrology calculations, again, at the scale that land development is happening. So we're showing here some catchments in our downtown watershed in Roanoke City, on the order of acres to maybe tens of acres, with curve number calculations shown there in red to yellow spectrum. Let me go back to the importance of this data, and just showing how understanding even where the watershed is requires this in urban areas. So you'll see as I flip back and forth how the new data. So actually the one I have shown here is a watershed delineation from 1997 using the land surface topography only. And as I flip backwards, you'll see how when we use that higher quality LiDAR data and integrating the storm drain pipes and inlets and manholes and sort of everything involved in that drainage system, the watershed shape actually changes. So even knowing where the watershed is requires a pretty high level of data collection. So let me kind of summarize some of the things that we've talked about as we continue on with our stormwater big data topic. We have to know where the streams and storm drains are in our system. We have to know where the inlets and pipes and manholes and every appurtenance is and how they drain. We also need land surface data on the order of meters or maybe parcel scale. So pretty high resolution. Water quality and quantity data at time steps that are appropriate for the processes that are happening in urban watersheds. So sub-hourly and inspection and maintenance records, again, of these urban stormwater features, of these pipes and manholes and so forth, over time. And you can see some graphics that I've pulled there, various parts of the data collection process. Okay, so we've talked about the need to gather the storm drain information. So how do we actually do that? How does that information become available? So I'll show you some examples. Again, this is from Roanoke City, acknowledging that there are other companies and organizations that have developed similar methods of gathering infrastructure data, asset management, and so forth. In any case, this is how we've schematized it here with our local governments, and just to give you an idea of what's the level of detail that's necessary.
We're doing it in Blacksburg. Have been doing it in Blacksburg as well.
Indeed.
Yeah.
So the graphic shows an iPad. So this would be something that a field staff for one of our local governments would have. For example, they would have a mobile app. We use ArcGIS collector for this. So the field worker would be out surveying the infrastructure. They'd find a manhole and inlet, and it's schematized, of course, as a point feature class or feature layer. The stormwater BMPs, the best management practices, typically a polygon. We attribute different information to these feature classes. So for example, what type of BMP is it? Is it a bioretention cell or a detention pond or otherwise? Various dimensions and other important hydrology and hydraulic information is, again, part of the data collection process. And then, of course, the pipes are schematized as lines that connect the points to each other. And, of course, the direction and the connectivity of this is really an important thing. You can really think about the National Hydrography data set. It's similar in concept to it, in that we have a node conveyance system, but we're just, of course, talking about a much smaller scale. The field users would typically be interacting with a tablet or a mobile phone of some sort, and with kind of the advancement of cloud-based workflows and GIS, one of the really nice things about having that is that field users can send their information into the cloud, which can then interact with local servers. GIS staff in an office can perform more complex analysis and geoprocessing on that data, maybe not exactly at real time, but at near real time. And then we can, of course, have interfaces for the general public and internal users to be interacting with that cloud data through permission-controlled browser-based interfaces. So this is kind of an example of how here locally we have it set up. Of course, there's many different ways to do this, but just to give you an idea of how that information comes in the door and is used for stormwater management. So let me summarize the past couple of slides. The storm drain infrastructure is typically schematized as a vector feature class or feature layer. We have pipes as lines, pipes, ditches, and streams as lines, inlets, manholes, pond outlet structures as points, and stormwater BMPs as polygons. Our workflow allows us pretty robust access control for the various levels of users. This type of interface has the advantage of being able to move data from the field to the desktop pretty rapidly. This sort of interface would be used for the inspection of outfalls, which again is the location where the storm drain intersects the stream. Of course, it could also be used for asset inventory, which if collected with a database that's appropriately set up can then be used for H&H modeling. And one of the other things that we'll talk about here in just a minute that Dr. Hodges will present is how this type of system can be used for BMP inspections and other things.
As Mark had mentioned before, we realized that developing this kind of data, is not totally novel. There certainly are a number of companies. I can think right off the top of my head, CityWorks and Cartograph are two, but there's quite a few, and a number of consultants that have done this type of work as well. But we've had the advantage here of working with a couple of Phase 2 MS4s and being able to work with them on this. And in fact, a number of my students have gone on to work for software companies. It's a wonderful thing to be able to work on the edge and be able to develop this kind of big data. But I know Clay wants to talk about some of the custom applications.
Right.
Okay, go ahead.
So Marcus did a good job of talking about ArcGIS Online and getting things up into the cloud, and then use of the Collector app, which I'm sure a lot of you are familiar with. What we found, though, is when we started to try to pilot a system of collecting BMP inspection reports in the field with the town of Blacksburg stormwater inspector, was that the Collector app really didn't give him what he needed in terms of being really efficient in collecting those inspections. There were some complaints about the size of the fonts, that sort of thing. So what we did is a little bit more research into it, and Esri has a product, as Randy mentioned, I'm sure there are other software companies that have it as well, that can communicate through Collector and actually directly communicate with the feature service that's online, and it really gives you a much cleaner interface. So you can see an example of that on the right, where the inspector would enter the inspection date and answer a few simple questions about the particular area he is inspecting. It's a lot easier to use, and it really gets to the needs that those employees would need, those staff would need in the field. Now, once they collect the data, and it's all in the cloud, remember, they get back to the office, and the next task that the inspector has is producing letters to go out to owners of particular parcels. And those forms usually are populated with things that need to be maintained, and so there are bullet points in a certain format. And they ask us to develop an app that would allow the inspector to just use a very simple program on his desktop, put in a date range. It would auto-populate using the data he collected through the Survey 123 app. It would auto-populate those bullet points, and they could really speed up the process of writing these letters. The ArcMap software development kit allows you to do that because it gives programmers the ability to program custom apps that are interfacing directly with those online services to really customize the process for the end user. So we've also talked about a lot of data that we're collecting. So we get all this data into the office and we have lots of IDs to deal with. Pipe directions could be erroneously put in. The nodes and the lines might not snap to each other. So what do? We go through and scrub the data, and we've automated that process to a large extent using Python scripting. It's something that our group has really started to use over the last few years, and it really speeds up these iterative processes of going through the data and making sure it's good data. Here's an example, we're not going to dwell on this, of a script that we did to aid us in looking at the distance to inlets. It was for a particular analysis we were doing for erosion risk. Again, we're not going to dwell on it, but this just gives you an example of the flowchart type mentality that we would have when programming a Python script. We also collect other data. We've talked a lot about geospatial data, but there's a lot of data out there, and some of it would be things like NOAA precipitation data, stream gauge data that is available online, and we've used custom scripts using languages like R to automate the process of going out and pulling in that data. Here is an example of a NOAA precipitation retriever app that we're actually still working on developing. That's a graphical user interface on top of R, which I'm sure a lot of you are familiar with. And we're doing a lot of work in this arena to try to make sure that the end user has the tools to quickly pull this data out from online, because it's really hard to find it and really hard to pare it down. So what is our group using the big data for? Well, we're using it for stormwater modeling, such as scenario modeling, using a variety of different hydrologic models. We're using it for hydrologic and hydraulic analysis. We're using it for watershed master planning, which Marcus has talked about a little bit. And we're also using it for risk mapping. We're going to give you a few examples of some of these. We're not going to dwell on them today because our future speakers are going to talk in more detail about it. But we just want to go through a few of those so you guys know what we're working on. This was a study that was done in Fairfax, Virginia, to look at the runoff characteristics of a few BMPs that were in place, and there was some monitoring and then modeling in SWIM to determine what the capture efficiency was of those and the treatment. This is also looking at BMPs. This study and the next study, which I'm going to go ahead and go to, we're looking at the runoff reduction characteristics in a particular watershed in Blacksburg, Virginia. If you guys are interested in reading more about these, we have the links directly to these papers down at the bottom of the screen.
Yeah, I should point out that CUAHSI has this whole presentation as a PDF, and I'm sure if you're interested, they'd be happy to ship it to you. So the links are active.
Right. This was a study looking at quantity control and looking at 7 different methods of reducing flood peaks in watersheds, and it again analyzed data in the Blacksburg watershed using all the infrastructure that we collected through the system. And then Marcus is going to talk a little bit about an uncertainty study that we worked on.
Thanks, Clay. So as we went through the process of building models and using them and calibrating, what we realized is that some of the sensors that we were using to calibrate our models against, so the photograph on the bottom right is kind of a typical storm flow sensing setup. Some of these sensors were giving us some erroneous or seemingly erroneous measurements. So we did a study where we put these sensors in a hydraulic flume in a laboratory and compared them to benchmark values to try to understand how much uncertainty is associated with those sensors. Again, the paper is available at the link at the bottom. As we started thinking about uncertainty in the sensors, it also occurred to us that in the treatment of stormwater using BMPs, there's a pretty wide range of performance variability in terms of the mass load reduction values for the different types of BMPs. So I won't go into the details of this graphic, but that's another sort of research thing that we're working on is how effective are these BMPs and what sort of uncertainty ranges are we looking at when we're using them. The use of BMPs and of course the modeling efforts kind of all come together in watershed planning. So thinking about how to invest capital money wisely across watersheds, across bigger areas. The graphic that you see there is another watershed in Roanoke City up the road, showing the distribution of BMPs across that watershed. So this data and the analysis that we do on the high resolution data gives us information that helps make good decisions about capital spending, maintenance spending, investment in BMPs, local policies, and so forth. You can again see the links to or not the links, but the references to a couple different reports and papers. One of them is in review there at the bottom. As we have gone through the watershed planning process, what we've realized is that attempting to really increase efficiency in spending and operations leads to some complex research questions. So what I have shown here is a research paper that we wrote a couple of years ago, or last year, I suppose, with looking at how do we target illicit discharge detection. So trying to find places where pollutants are going into the storm drain system that shouldn't be going in. You can see a heat map there. We took a bunch of different GIS layers and used some geostatistical analysis to try to understand how better to target those inspections. And we've done similar other risk maps that Clay will now present to you.
Yeah, so the last year or so, we've also done risk mapping to look at thermal pollution. So we are evaluating watersheds and determining which areas of the watershed have the highest level of thermal risk using various data sets. We've also done something similar recently. This paper is going to be probably published this year of looking at erosion potential risk in another watershed in Blacksburg, Virginia. So this one is, again, evaluating cells relative to each other, not trying to track actual soil migration through the watershed, but trying to determine the various areas of the watershed that have the highest risk.
Okay, let me try and summarize and give a few conclusions to what you've seen here during our discussion here in my office. First off, it's a big topic, and we are talking about big data. We tried to kind of go from the national water data model to the urban stormwater, and there's a lot of data here. We think what it can do for us if we do it right is reduce flooding and improve our water quality, our ecosystems, our quality of life. We think that that's the case. You've seen a lot of GIS data sets. They make pretty pictures, but it's a lot of data. But we need that if we're going to make better decisions at the local level. And that's where we are in the urban environment. We're at the local level. In doing so, you have to have rigorous protocols and methods for collecting, storing, processing, analyzing all of this data. If you don't do that, then it's just data that may not match other data that you collected last year or the year before. So consistency in data collection is quite important. You have to use nationally available data and local data. Very frequently what you want is not available. So you have to have a way to collect that data and do it well. So we have to understand what that data is. So once you get data, it's not necessarily good data. So analysis of that data turns it into information. So that's quite important. Secondly, making that available to the people that need it is quite important. And then making use of that adaptive feedback loop improves the value of the money that you've already invested. And lastly, we think, and I hope we've shown you, that there are a lot of different areas for some very cool research in collaboration with the municipal governments. And governments of all sizes, as I've said here, both phase 1s and a lot of phase 2s. And those phase 2s, you know, there's a lot of need out there. They don't necessarily have the amount of resources that phase 1s have. But it's fun working with the phase ones too. So I encourage everyone to get involved. There's a lot of work that needs to be done. This is the first of 4 what I think will be very, very interesting webinars. I wanted to just close with some very inventive, creative Hollywood posters that one of my master students kind of put together for us. These 2 photos were taken from some of our explorations in the tunnels of the city of Roanoke just last year, and she thought they were worthwhile kind of putting together as movie posters. so the Tunnel Invaders there, followed by the sequel. But we'll stop there and see if anyone has any questions. So at this point, I will see if there are any.
All right. Thanks, Randy. We do have a few questions that have been coming in. One is from Aditi Bhaskar, who is asking, how did the partnerships with the MS4 permit holders get started? Did they approach you with their data analysis needs?
Yeah, that's a really good question. I have to admit to being a little forward and asking them if we can help them. Making contacts, developing relationships, seeing what they need, and also showing what we can do for them. And of course, letting them know that we have some wonderfully talented students that can help them. That's how it starts. And then once you prove to them your value, it just kind of grows. I think, guys, you want to add anything to that? I mean, they're nodding their heads, but you can't hear that.
Yeah. That's good, Randy. The only thing I think I would add is that the localities that we've worked with are, so far at least, mostly Virginia localities. So I think it just helps that we have sort of a tight connection with them. For Blacksburg and Roanoke in particular, we're able to really spend a lot of time in their watersheds and really think about those as our laboratories. We're going and doing our work in them. We have students in them, and it's really been a great experience learning urban stormwater management like that through the lens of our municipal colleagues.
Yeah, although we've worked with Fairfax as well.
Sure.
There's a limit to how many municipalities we can work with. That is a true statement. But we have a lot of students. Many of our students come from Northern Virginia, and so there are relationships there automatically. Mm-hmm. Clay, you wanted to mention?
Yeah, I did want to mention that we have, on occasion, made a summary presentation of all our research and gone to different municipalities and given a presentation just to let them know what we're doing. And in Fairfax, for instance, that turned into several research projects that we're working on now.
And that's true. Yeah. And in fact, we did it with others as well. And so there's a limit to how many we can take on. We've actually had several approach us that we couldn't handle because of the limit of the number of students that we did have. So yeah, good question. Thanks, Aditi.
Great. We have a few questions coming in about accessing some of the reports that you mentioned. So Mary Santelman asks, would it be possible to access some of the technical reports cited in the presentation too, which may be difficult to get, perhaps a shared drive that you could send the URL for?
Yeah, I would just ask, maybe you can funnel those to me, Emily, and then
sure.
If there's any commonality in the requests, then we can handle them all at once.
Sure. So I will put my email address in the chat box if anyone wants to access anything in more detail.
Right. And as I mentioned, you have the PDF of this whole presentation, and the links for the papers are all active. And my own web page for Virginia Tech under the cee.vt.edu webpage, all the papers under my webpage are active if you have access to some of the journals. But all the reports are not necessarily online. I might have to dig for some of those.
Mm-hmm. Now, Randy, can I post that presentation publicly, or would you prefer that people contact me individually for it?
Yeah, I think it's fine to post it publicly. It might be easier for you.
Okay, so I'll put the link.
It might be good, to post it somewhere if you're going to be posting all of these under the winter webinar series. It might be just good to put a page up there.
Yeah, so what will happen is we will post the recorded webinar from today in our Cyberseminar archives, and I will also attach the presentation to that post. So it won't be up until later this afternoon or tomorrow morning, but you'll be able to find it in this link that I'm just putting in the chat box. And I also put my email address in the chat box if anyone has any additional questions or can't find that posting.
That would be very helpful.
Yeah. Let's see. So is there a depository with available national data and local data, especially BMP data?
Is there a repository for national data and BMP data? Is that the question?
Yeah.
Yes.
I think it depends on what sort of BMP data you'd be looking for. If you want spatial data sets, probably your state government, maybe not, I wouldn't say probably, but in a lot of cases, the state government would have a collection of where the BMPs are. In terms of BMP performance data, I would look at the International Stormwater BMP database, and you could just Google that one, and it will come up. That database provides the actual data, the performance results of a lot of different BMP studies that have occurred across the U.S. and I think Canada as well.
I don't know if that helps.
Okay. We have another question. What is your definition of big data? To my understanding, a lot of data do not equal big data. Big data usually exceeds structured databases capacity and have to use an unstructured database, meaning that if you can save the data in a GIS database, these are not big data.
There's big, bigger, biggest. That's why I entitled that section of the talk as Water's Big Data. So, if you want to, limit this talk to, urban stormwater infrastructure, hydroinformatics, we don't have a really good feel for how big this data really is. If we were to compile all of the data for all of the urban infrastructure of the United States, we honestly don't know how big that data is. So all I've been able to talk about here, I gave examples of Baltimore and Fairfax. As we saw before, there were 6,700 MS4s and 858 phase ones. If we were to compile all the data, and not just the infrastructure data, but all of the attributes of the infrastructure, all of the workflow of the infrastructure, I would hazard a guess that it's not able to be handled in a GIS. I think I'd be pretty safe in saying that. And I think it's a hypothetical question anyway. It's big data. There's a lot of urban stormwater data out there, especially as we start doing hydroinformatics and we're collecting water quantity, water quality, and weather data on the resolution of 1 to 5 minutes. And now we're talking about it perhaps hundreds or even thousands of points in every city. Yeah.
All right, so we have a few more questions coming in, if you don't mind staying on the line a bit longer.
Sure, go ahead.
Great. We also have some nice feedback. Thanks for a great start to the series. But here's a question. A lot of the modeling shown didn't really talk about BMP performance, which, as the speakers pointed out, can vary tremendously. How do you handle the uncertainty associated with BMP performance in your modeling?
That's an excellent question. I think the moving from the empirical uncertainty into how to use that to make management decisions about spending and about just deciding which BMP to use over one over the other. That's kind of at the front of the research right now. We recently finished the article that you saw there on the screen. I guess I can't say we finished it, but we're sort of waiting for another review on that paper. And I think the next move is, once we've established the empirical uncertainty in BMP performance, and we've sort of built a framework for how to think about that, the next move is to look at how does that uncertainty, how do maybe the probability distributions or the probabilities of failure, or however you would frame it, how does that get incorporated into management decisions? What is a reasonable way to do that as we start looking at big basin scale TMDLs and local TMDLs? And the question of how effective are the BMPs that we're spending money on is I think on the forefront of lots of people's minds. So I guess I don't have an excellent answer for that, except that that's probably the next thing that as researchers we'll be working on, is how to take the empirical uncertainty that we've established and incorporate that into the decision making process.
Yeah, I think you're exactly right. With that paper, I think we'll be establishing empirical uncertainty, and where do we go from there? That's on everybody's mind. A lot of money, as I said, that people are spending on this, and do they work or don't they work? And there's a wide range of uncertainty that we've seen in our work.
Great. We have another question from Stu Schwartz that says, NRCS guidance cautions that no supposition based on natural soils will accurately reflect hydraulic properties of disturbed urban soils. Therefore, field investigations must be made. We commonly find compacted, disturbed urban soil profiles in developed, mass-graded landscapes that produce almost as much runoff as our impervious areas. Yet, we routinely use StatsGo and Surgo soil properties in distributed models in urban landscapes without questioning the soil profile properties. Given the inherent equalinity of distributed models, can you address the inherent uncertainty in soil infiltration characteristics in higher resolution models of urban hydrology?
I totally agree. I think it's a very well phrased question with very important points that are raised. The recent stormwater laws that were passed in the Commonwealth of Virginia really force us to use the NRCS equations, and we don't have a substitute any longer that we can go to. Clay, I know that Clay has worked as a consulting engineer, owning his own firm for 20 years. Stormwater as his specialty. Let me ask Clay to take a shot at that one too.
Yeah. So
thank you for that question. It's right on point.
Yeah, it's actually a really interesting question. So basically, what it boils down to is there are soil maps that were created using very little in the way of data points, and engineers blindly are using those maps to determine what the hydrologic soil group is and creating runoff. When you get into urban areas, though, by and large, soils fall into a classification called eudorsants, which basically means it's mixed up soil from all sorts of different sources and compacted highly. If you are thinking about the hydrology, really as an engineer, you should go ahead and most likely use the hydrologic soil classification of D when you're analyzing those, which generates the most runoff. Do most engineers do that? Probably not, but that in reality is what's happening, and I think that's the crux of that question. So it's right on target. Municipal engineers, when reviewing plans, need to be aware of that. And if the engineer is stating that it's getting a higher rate of infiltration, then there needs to be soil tests to back it up, in my opinion.
Yeah. Thank you for that. That was well phrased and exactly on the point that we've discussed multiple times here. We do an awful lot of coursework and research in the land development area, so we're very well aware of that.
All right, we have 2 more questions that are in the chat box, if you want to take those. And
let's do that, and then we'll probably should close it up here.
Yep, we'll close it up, but if any other questions come in, you can contact me directly and I can pass them along. So here's a question from Kate McNeil. Are the speakers aware of any papers that elegantly address BMP performance on benthic macroinvertebrates? I'm familiar with many regarding the intermediate responses, flow, water quality, but few actually getting at biological responses with BACI designs, paired basins, etc.
There's one in my brain, but I off the top of my head, I'm not going to be able to give a citation. I would also add that the processes that drive the diversity of aquatic insects, part of it is watershed driven, and the other part of it is a local sort of a stream reach driven issue. And so in terms of performing that analysis, it makes it really hard to tease out, are the BMPs doing the work, or is there some other local or stream reach factor that's doing it? So I guess I'm not going to say that there isn't literature on that. I think that there probably is, but if I can think of one, maybe I can pass it along. Off the top of my head, I'm not going to be able to throw out a citation for you, unfortunately.
Well, let's ask the questioner maybe to send her email to Emily, and then we can perhaps send her a reference if it comes to you. Okay. Yeah.
Okay, great. Thanks. And then the final question from Aaron Morrison. Does your modeling incorporate infiltration or Darcy's Law? If so, what software do you use?
I believe that SWIM actually has the ability to model that. I actually did not oversee that modeling effort myself, but I'm pretty sure that Brett and Matt both use infiltration built-in functions in SWIM or sewer gems to do that.
Yeah, we did. This is now a few years back, but there is in SWIM and in Bentley sewer gems, there are infiltration functions built in, and you can put in your rate directly. I don't know if that helps or not, but the answer is yes.
All right.
Yeah.
Okay. Well, thank you, Randy and Marcus and Clayton, for an excellent kickoff to our Cyberseminar series on urban stormwater hydroinformatics. And as a reminder to everyone that's on the line, we will meet again at the same time next Wednesday, February 14th, where we will hear from Branko Kirkes at the University of Michigan regarding enabling smarter urban watersheds. And again, if you have any questions or you'd like to see the recording to the presentation or the PDF version of the presentation, feel free to contact me directly. My email is eclark@CUAHSI.org. So thank you again for joining, and thank you, Randy, Marcus, and Clayton.
All right, thanks, everybody. Appreciate you tuning in. Bye-bye.
Bye-bye. Have a great afternoon.